Welcome to this explainer. Today, here in June 2026, we are diving straight into something truly mind-bending. We're looking at how AI is finally, and I mean finally, serving a truly global audience without needing endless mountains of data for every single language on Earth. We're peeling back the curtain on modern NLP to see how software is actually scaling to the rest of the world, way beyond the usual high-resource languages. Okay, let's just address the elephant in the room right away. If you want to build global software, you're immediately going to hit this massive, frustrating data desert. Think about it. English has literally billions of labeled examples. You can find high-quality training data for almost any niche task you can dream up. But then, you look at a language like Urdu. You might only scrape together a few thousand examples. And for a language like Maithili, you're looking at almost nothing, zip, zero. So any practical, real-world NLP system has to figure out how to survive in this long tail of languages where task-specific training data simply does not exist. But hey, there's a way out of the desert, and honestly feels a bit like magic. Cross-lingual transfer isn't just some neat optional feature anymore. It is absolutely the defining practical miracle of this decade for natural language processing. We can now train a single model on many languages simultaneously, completely bypassing the need to hoard a mountain of data for every single dialect on the planet. Here is our roadmap for today. We're going to cover the multilingual NLP miracle, dig into how it actually works, trace the model timeline, reveal the source language secret, expose the hidden tokenization tax, and wrap up with exactly how you should build, evaluate, and ship. Let's get to it. Section 1, the multilingual NLP miracle, or how we are solving the global data drought. Okay, picture this. You take a model and you fine-tune it entirely on English sentiment analysis. It spends all its time learning what positive and negative reviews look like in English. Then, you flip a switch and feed it text in Urdu. And suddenly, it can accurately predict sentiment in Urdu right out of the box. It has literally never seen an Urdu labeled during that fine-tuning process. No way, right? But it works. That is the core of zero-shot cross-lingual transfer, and it has absolutely revolutionized how we ship tech globally. Section 2, how cross-lingual transfer works. Let's look under the hood of this miracle. So how does this actually happen? Well, it boils down to a pretty crucial three-step process. Step 1 is establishing a shared vocabulary. These models use tokenizers trained on text from all the target languages at once. Because that vocabulary is shared, the exact same subword unit can represent the same morpheme across related languages. A great example is the prefix anti. It gets the exact same token whether the model is reading an English document or an Italian one. Which leads us perfectly into Step 2. Shared representation. By training on masked language modeling across hundreds of languages, the transformer essentially learns that semantically similar sentences should produce similar hidden states. In the model's vast mathematical embedding space, translations physically land right next to each other. The embedding for the English word cat clusters right alongside chat in French and gâteau in Spanish. Because the model inherently gets that these words occupy the same conceptual space, applying the actual skill, which is Step 3, across different languages becomes totally possible. Moving to Section 3, the timeline of models. Let's look at your multilingual arsenal. Tracking the evolution of these models is like watching a sci-fi movie unfold in real time. We started back in 2018 with mBird, trained on Wikipedia across 104 languages. It was totally groundbreaking at the time, but, kind of weak on low-resource languages. Then, bam, 2019 gave us XLM-R, trained on a massive Common Crawl dataset, which became our gold standard baseline. Fast forward a bit, Meta drops NLLB-200 in 2022, pushing translation to 200 languages. 2023 brings us XLM-V with a whopping 1 million token vocabulary. And that takes us all the way to Cohere's incredible IA-23 generative model in 2024. This timeline proves just how insanely fast we've expanded to cover the long tail of the world's languages. And here is your definitive 2026 deployment stack. You really don't need to guess anymore. The community has figured this out. Pick XLM-R base as your sane, everyday default for classification tasks across 100 languages. Doing translation? Grab NLLB. Doing generative LLM-style work? IA-23 or MT5XXL are exactly what you need. It's all about picking the right tool for the specific job. Section 4. The source language secret, or why English might actually be ruining your fine-tuning. I really want you to stop and ask yourself this question. Should you default to English as your fine-tuning source? I mean, the gut instinct is usually yes, absolutely, because English has the most training data by a mile, right? Well, actually, scratch that. Defaulting to English is proven to be the absolute wrong move for a lot of target languages. Recent research has uncovered this fascinating secret. Language similarity predicts transfer quality way better than raw corpus size. If you fine-tune on English, you're often going to get weaker transfer when aiming for distant languages. So, say you want to deploy a model in a Slavic language. Fine-tuning that model on German or Russian will often completely crush fine-tuning on massive English datasets. Targeting Indic languages, fine-tuning on Hindi is for sure your best bet. So, how do you actually choose? Seriously, don't just guess. You should be using similarity metrics to figure out your best source language. You can use the 2019 Lang rank, which ranks candidate source languages by looking at linguistic similarity, corpus size, and genetic relatedness. Or you can jump to the newer 2026 QWALS metric, which quantifies similarity based on the World Atlas of Language Structures. The golden rule here is simple. Find a typologically close, high resource relative to your target language and fine-tune on that first. Section 5. The hidden tokenization tax, the silent killer of low-resource NLP. So multilingual models share a single tokenizer, right? And that vocabulary is trained on a giant pile of text completely dominated by languages like English, French, and Chinese. For any language outside that VIP club, you get hit by 3 compounding taxes. First up, the fertility tax, where low-resource languages are shattered into far more tokens per word. Second, the variant recovery tax, where even minor typos or Unicode quirks become totally unrecognizable sequences because the model just doesn't know the basic orthography. And third, the capacity spillover tax. This is where those first 2 taxes secretly eat up your model's reasoning capacity, leaving way less room in the context window for actual useful logic. To give you a real sense of how brutal the fertility tax can be, just look at this multiplier. 3 to 5 times. A single sentence in Hindi can require 3 to 5 times as many tokens as the exact same sentence in English. Let that sink in. That is absolutely devastating. It instantly devours your context window, it tanks your training efficiency, and it completely blows up your latency budget when you try to deploy. The really sneaky part, your model might seem totally fine. Your loss curve during training looks perfectly healthy. But out in production, the outputs are just subtly off. Rare inflections just collapse mid-sentence. You have to remember this. You cannot data scale your way out of a broken tokenizer. If the fundamental way the model reads the text is broken, just blindly throwing more data at it won't fix the structural disadvantage. Don't panic, though. You can fix this before it turns into a disaster. First, pick a high-coverage tokenizer right out of the gate, something like XLM-V with its massive 1 million token vocabulary. Second, you absolutely must verify the tokenization fertility on your target text before you start training. Check your work. And third, implement byte-level fallbacks for long-tail scripts. You want to guarantee that absolutely nothing registers as an out-of-vocabulary error. Finally, Section 6, Build, Evaluate, and Ship, your blueprint for global deployment. Listen closely here. Aggregate scores are lying to you. When evaluating these models, never just look at the high-level average. A good average will easily hide the long tail of failing languages. You have to evaluate per language accuracy on held-out sets. Also, benchmark against monolingual models just to verify your fancy new multilingual setup is actually better. Make sure to run entity-level tests directly, because tokenization loves to fail on names in non-Latin scripts. And lastly, check for cross-lingual consistency. A sentence with the exact same meaning in English and Arabic should spit out the exact same prediction, every time. And if performance really matters, which, come on, it always does, always budget for few-shot fine-tuning. This is basically a cheat code. You don't need millions of rows. Adding just 100 to 500 labeled examples in your target language, using a very low learning rate around 2E5, is the absolute most cost-effective level you can pull. Doing this can shoot your accuracy straight up to 95 or 98% of your English baseline. Just keep that learning rate low, otherwise you risk destroying the multilingual alignment you've built. I want to leave you with this thought to ponder. We really have achieved a practical miracle with cross-lingual transfer. It lets us build for global populations faster and more efficiently than anyone ever thought possible. But if zero-shot transfer is merely a starting point, just a brilliant stopgap, what is your next step to ensure true language equity in the software you build? Are we just going to settle for good enough for low-resource languages, or is there an even bigger leap ahead? Think about how we can use these tools not just to translate, but to truly understand. Thanks for joining me on this explainer.